So this Thursday, when we go to the lab, you're going to get to see friction stir welding, hopefully. You're going to see also other demos. So that was last class. Anyway, so about friction stir welding. We discussed this last class, and I discussed a little bit. So first of all, is there any protection for the melt in friction stir welding? No, right? Why? There's no melt, right? It's a solid state process, and that's the whole point, that we don't want to melt, and this way we do away with the problems of solidification, right? So in this case, we have a pin that rotates, and what happens in this process is that we have localized deformation that is coupled with localized heating, right? And in the right conditions, this just gives us like a cross-section such as this, right, in which this part was affected by the heat, but this part was heated and stirred, right? And the characteristics is, which we discussed briefly, this works with low temperature alloys, and the reason is that the pin gets very hot, right? The aluminum, for example, if we do aluminum, gets hot but gets soft, but you don't want the pin to get soft, right? So I can use a steel pin for doing aluminum, but what do I use to weld steel, right? Eventually the periodic table runs out of materials with the right properties, right? And we discussed some of the things like the need for having very good fit-up tolerances, and also that we need a very stiff machine. So when you go to the lab, and I still don't know exactly, I think we have a demo prepared, but you see this enormous milling machine. Remember when you came and saw the demos on TIG and PTA, right? This huge milling machine is for doing friction stir welding. It needs to be very rigid. Arc welding doesn't need to be rigid. So I showed you this video about, right, the tool is rotating, plunges in, and then starts moving. So let's see, when it comes in, it's going to go. What you see there is a reflection on the shiny aluminum. There the tool went in. All right, so I want to show you another video of people trying to weld pipelines, right? Now it's interesting. So just to gauge your intuition, I don't know what they are using for welding the pipeline. I think it's some crazy ceramic like or nitride, I don't know. It's a very, very sophisticated materials, very expensive, right? And if you weld steel, right, and you want to cause a localized heating, what would be a especially important temperature to reach in steels, like pipeline steels? What would be a key temperature you want to reach? 1600 would be pretty interesting, but melts, right? So for friction stir welding, you do not want to reach 1600 for sure. Okay, I like that one. Why? It's not eutectic. Eutectic temperature is when you start austenizing, right? So okay, so you start to generate austenite. And why do you care about austenite?
So you can redefine your grains or depend on your cooling rates.
Maybe. Okay, some of the Maris come to the rescue. Why would I want austenite in friction stir welding?
Because you want everything to be in one phase.
Okay, but I could, if I'm at 500 degrees, I'm all in one phase. Or kind of, right? Okay. So it wouldn't be one phase, but those carbides we can deal. Okay. So, okay, for the math is here. Friction stir welding, that is a solid state process, is hot working, right? What is the when you are doing hot working in steels, for example, forging? Is there anything special about temperatures in forging? All right, yes? What? What is special?
To raise the temperature, or maybe either apply it to beat the ball.
I'm worried. All right, we're going to forge steel. I'm going to forge it at 600 degrees or 900 degrees, right? Clearly, hotter is softer, right? But why is it so important to go to that temperature?
Without work hardening.
Okay, so in steel, at low temperatures, you have ferrite. Ferrite is BCC. FCC, right? You go to austenite. So I'm worried. I don't want this to happen. We have a whole bunch of Maddies here. You Makey are forgiven, but guys, right? Like this is in steels, temperature is for hot working is essential because once you're in austenite, we are in the FCC crystal structure that has all these convenient slip planes, right? And then we can deform it. So once you reach austenite, it's a lot easier to deform things, right? So most hot working processes in steel are in austenite. Okay, but I was just leading into my point. So if I'm doing steel and I want to reach austenization, what is going to be the color of my tool? It's red hot, right? Right, because we're at like way above in the range in which things are glowing red hot. So I wanted to bring this up before I showed you the video, so you start having a sense about what to expect even before you see it, right? I think it's very important for us as engineers to be able to anticipate the world before we see it, right? Some people just need to do an experiment to see it, but every time you do an experiment, you spend time and money. So in our case, we would know what to see. So that's a pipe. They're putting the equivalent of the anvil, right? They're putting a backing tube because the friction stir welding presses against it. So this is for the backing. They put the pipe. They grind it. Right, now you have something that is tight against the pipe, so the friction stir welding can push against it. By the way, this is not a common process. I saw this video and I'm showing it to you, but it's not that people are doing this every day. You see, this is the weld as it is moving. And it's moving very fast. But let me tell you that this is moving way, way faster than you would if you were welding it by hand. I believe there is a take here. That's a tool, right? Let me tell you, if your tool was some sort of normal steel, that it cannot take that, right? So typically they are ceramics when you're welding with these very high temperatures. Why do you think they're putting that wedge there? Actually, what is going on is you have the pin inside the steel. How do you stop the process? How do you stop it without a hole? Right? That's why they put this wedge. So they tail out over the wedge. And then they come and they are going to grind the wedge. right? Because that's one of the problems of friction stir welding. Like, because it's autogenous and it's solid state, you end up with a hole where the pin was. Whatever you do, you want to get the pin out, but it doesn't have liquid that flows back in. Right? So, if you could do this all the time and reliably, it would be awesome, right? But this is not the way we weld pipelines today. But as you see it, if you could weld like this, would be a fantastic thing. Would be semi-fantastic. If you weld this fast, you still have to, all the inspection and all the logistics that was tailored for the normal welding speed. So if you move one thing faster, everything else needs to catch up now, right? So it's a propagating process. All right, that was friction stir welding. Look at our machine next time you're in the lab this Thursday. I want to talk about friction welding. Friction welding is a fairly old process, and the way it works, we have these 4 stages. In stage 1, you have one part. Typically, you have parts with a circular cross-section, right? So one of these cylinders is rotating, and the other cylinder is stationary. That's OK, and you get up to speed. Somehow you can get up to speed because you have a motor. You can get up to speed because you have a flywheel and you have loaded kinetic energy in the form of inertia. In stage 2, you bring these 2 cylinders together, right? You can do this in a lathe, right? People have converted lathes for this. So you move this other part, and guess what? Similar to friction stir welding, with a very similar principle, what you have is the friction generates localized heat, right? Right at the interface. And this heat is going to soften it, and as it softens, it also generates heat, right? So you have this very localized plastic zone right at what used to be the interface. And as you put pressure, right, as you keep putting pressure, you start extruding out the hot part that is also soft, starts extruding out and makes this upset here, right? This burr coming out. And then you stop it. And things cool off, and they are just fine, right? So this is a way you can weld cylindrical parts, and they don't need to be solid cylinders. They can be, for example, a hydraulic cylinder that is a tube with a cap, right? Many things that have this type of geometry you can do. And they don't need to be always the same material. They can be dissimilar metals that if they are compatible, they don't need to have special solidification properties, similar to friction stir welding, right? You would join them without having like issues of segregation and hot cracking. So this is an autogenous process, right? Although everything has an exception. People have tried doing this, putting some like plate in the middle. You can do so many things and be creative. But for the most part, for the large part, this process is autogenous. You can do this like friction surfacing as it rotates and it kind of gets upset and it's upsetting. You can move it over a surface, right? Not very common, right? But you can use it for surfacing. When you have rotational motion, right? In this case, is rotational motion an actual translation to create the upset? The rotational motion, I mentioned this before, can come from a flywheel that accumulated kinetic energy, right? That's one way, or the other can be a motor that is constantly putting energy. From the point of view of the fundamentals, is more or less the same. From the point of view of application, people would find quite a bit of difference between one and the other. Now, the motion doesn't need to be just circular. For example, if I needed to weld 2 things that are rectangular in cross-section, instead of rotating it like this, I can rotate it. I can have a relative motion, like back and forth, right? That is what is called linear friction welding. So much as before with friction stir welding, works well with many alloys, even that if they are unweldable. There is something different with friction stir welding, because in friction stir welding we have a tool. The temperature of that tool limits our process. Right? If the process gets too hot, the tool cannot take it. Now, in friction welding, there's no tool. You're grabbing the parts in the chuck, but that part is not hot. It gets hot only near the interface. So if you needed to reach 1,000 degrees, you don't care. You're fine. Right? Friction stir welding, you care very much. So of course, this is not a manual process, requires stiff and heavy equipment. I was once told, I would need to find information, if you're going to have 10 kilowatts of electrical power, it's going to cost you so much money, for example, in an arc welding machine. But 10 kilowatts of mechanical power are much more expensive, because you need the setup that is rigid, you need motors. So if you see this type of welding processes in solid state, you tend to see these huge machines with a big footprint. Right? Applications, this is shop welding. For rotating friction welding, for example, the shaft of jet engines, right? We talked at the very beginning of class how in a jet engine it has hot stages and cold stages. And the material you would use is different. And with friction welding, you can make a really good joint, as close to the no joint as you can imagine, between those two different alloys. Linear friction welding is used to attach blades to discs and make special turbine discs for the hot part. I'll show you two videos. I'm going to show you first a video about normal friction welding, and then I have three videos. I'll show you two on normal friction welding and one on linear friction.
In solid-state welding, coalescence is created at temperatures less than the melting temperature of the base metals with pressure. The two most used solid-state welding processes are friction welding and ultrasonic welding.
We'll discuss this later.
Friction welding is an extremely rapid method of welding workpieces, typically in butt joints, by frictional heat.
You see, as you press,
force.
all that is coming out. Huh? Okay, that's about it. So I'll show you another video. Really, was it? Did something happen there? No, I know what happened.
Frictional heat is generated by rapidly rotating a workpiece against a stationary workpiece until the interfacing or faying surfaces reach the proper temperature. The weld is completed by an upsetting operation which consists of the rapid application of additional axial force as or just after the rotation stops. This upsetting operation forces hot metal, oxides, and impurities out of the joint. In general, one workpiece must have an axis of symmetry and be capable of being rotated about that axis. Workpieces are usually either in butt or T-joints, with the pieces being bar to bar, bar to tube, tube to tube, and bar or tube to plate or disc. Additionally, friction welding can be used to join a wide range of similar and dissimilar materials, including most metals and alloys, some metal matrix composites, ceramics, and plastics. Ultrasonic welding is a method of producing.
I'll show you that later. Something funny. You know what you can weld using friction welding? You can weld wood. Would you believe that? And people have done it, and there are patents on that. So if you rub pieces of wood at the right speed and everything, it gets locally hot, and then there is a bunch of chemicals inside the cells that create some sort of like a localized glue. So again, it's not that you're going to start sitting on friction welded wood chairs, but that exists and has been patented. Isn't that awesome? Right? Who knew? Sometimes I was thinking, what would be the craziest thing to do? And I put welding of wood. And sure enough, something came up. If you talk about welding of rocks, funny, there is something called welded rocks. But it's not an industrial process. It's when rocks come out of a volcano, right? In some cases, between the temperature and the impact, they become welded. Isn't that funny, right? So welded rocks, welded wood. The world of joining is big. I wanted to show you this other video that is more or less more of the same. Where is it? Here. Phew. There you go. So somebody got excited with the handy cam, but there you go. They're going to rotate, right? And they're going to push. And you see the upset burr coming out here, right? Which you typically machine out. Look, that was spinning quite a bit, and then it stopped. Isn't this interesting? So funny enough, you're going to see later on a bunch of formulas, which we did for welding. And some of those formulas are based on the same principles with which you could calculate friction welding too. So, we're not going to do problems with friction welding, but we could if we wanted. All right, linear friction welding. Look, this is the way a normal turbine works. You have many blades, and the blades have a dovetail. You see that thing that looks like gear teeth, right? You slide it in, right? And that locks the blades into the disc, right? That's a way in which you can make many, many blades in one machine, and you can make the discs in another, and you put them together. Now, as you can imagine, the blades is where the action happens. The disc is just holding the blades. Everything that is disc and not blade is essentially wasted space and wasted weight. In a jet fighter, U is like a Formula One car, right? You want to waste no weight, you want to waste no space. So people have been thinking, how can we make these turbine wheels lighter? And one of the answers is using blisks, and that is the drawing on the photo on the right. A blisk is a mixture of blade and disc, right? Now, the blades don't come in with a dovetail because the dovetail is a waste of space and weight. They just weld it. Sometimes they cast it all in one, which is pretty tricky, or some other times they get these single crystals and they weld them on the disc, right? How do you do it? You do it with this linear friction welding. So this is not for a, by the way, I learned for this. I was doing this, preparing a keynote on a conference on aerospace manufacturing. They say, can you say something about welding? I said yes, but then I had to go and learn. And at the time, some people were doing this for jet engines, but nobody wanted to tell you this story. But if you hear partial stories from enough people, you start getting the picture all together. So now it's fairly well known that you can make these jet fighters turbine components with linear friction welding.
TWI has been interested in.
It's not as elegant, yeah?
It is ideal for joining blades to disc.
There you go. There you have the blisks. Of course, they're not going to show you how they do it for the blades to discs. You see, typically you would not do these pieces of that section with friction welding. Isn't that pretty amazing, right? So that is another form of welding in solid state.
question. You mean it's just that the part is not rotating, but it's actually moving this way.
Right. So when it's rotating, to some extent, you're forced to have a symmetry of revolution, right? But if you have other type of geometries like these rectangular bars, doing it, or the blades, right? You do it linearly, reciprocating. I think it's pretty cool. So about ultrasonic welding, right? This is autogenous. This is a welding process in solid state, but it's typically used for plastics, right? For example, if see that toothpaste at the bottom of the toothpaste, right? The people make this like big long tube. They put the toothpaste and they seal it using ultrasound, right? And it's super interesting because you have this. It's a little bit like linear welding, right? You have these oscillations that are very high frequency and they cause localized heating. Most things you're going to see that are polymers that are sealed, like the toothpaste, and you get to see those type of plastics. Those are ultrasonically sealed. Now, this is for high production environments, right? It's expensive equipment. You can do this too with metals. You can put strips of metals and what they call the sonotrode, the transducer that makes this ultrasonic motion, and you can weld one strip of metal on top of another strip of metal. And that is one of the many techniques of additive manufacturing in metals. So let's see if I'm forgetting something. Yeah, the very, very small displacements is autogenous. So I think here I have the video on. I have to go to 146 here. Okay.
Additionally, friction welding can be used to join a wide range of similar and dissimilar materials, including most metals and alloys, some metal matrix composites, ceramics, and plastics. Ultrasonic welding is a method of producing lap joints by high-frequency vibratory energy.
You see how it's leaving a weld behind? It's because that wheel was having these microscopic vibrations at very high frequency.
Interface surfaces with relatively little heat. The workpieces are clamped between two welding tips called sonotrodes or jaws. Vibratory energy is conducted through one or both tips, which oscillate laterally as a perpendicular force ensures contact of the workpieces. The oscillating action disrupts the interface surface films and permits metal-to-metal contact. This creates plastic deformation at the interface, resulting in a solid metallurgical bond. Under proper conditions, interface temperatures reach only 35 to 50% of the workpiece melting temperature. Basic equipment includes an electric power supply, a frequency converter to increase line frequency to generally 15,000 to 75,000 hertz, one or more transducers to convert that power into acoustical power of the same frequency, a coupling system to transmit the acoustical power to the welding tip and into the workpieces, a workpiece support system, and a force application system. Ultrasonic welding typically requires at least one of the workpieces to be thin. The usual welds are spot welds and straight or circular seam welds. Workpiece distortion is limited. Ductile metals in similar or dissimilar combinations are ideal workpieces, although hard metals also can be welded. Filler metals are not normally required, although they can assist in joining difficult to weld dissimilar metals. The electrical and electronics industries are the principal users of ultrasonic welding. Limited applications are also found in the automobile, nuclear, and aerospace industries.
All right, so that's quite interesting, right? Like so many ways of welding things. Something the video said that Aidan mentioned before is one of the parts needs to be thin, right? And the reason is, if you're going to have microscopic vibrations at very high frequency, if it is too thick, these vibrations would be attenuated before they reach the interface, if it is too thick. All right, solid state processes, explosion welding, right? And the casing that is magnetic pulse welding. In both cases, what you do is you accelerate the two surfaces so much so that you generate shock waves at the point of contact. So if you remember when we classified the joining processes, we mentioned that it's difficult to have a force applied that is higher than the yield stress of the material. The reason is because whatever force you put the material, so you cannot put any more force. Except in the case of explosion welding, because you have a shock wave. And the difference between the force you're putting locally and the force that the material can take, it becomes the acceleration of the metal in the shock wave, right? This was discovered I think it was after World War I, in which they would see some of the shells, the big like cannon shells, right? Like hit other metals and get welded super good. And they did a metallurgical analysis. And one of the interesting things here is that explosive welding is to some extent also a mechanical type of joining. So it's not bolts and nuts in this case, but the shock waves cause this undulation in the interface, right? And this undulation in the interface causes the materials to be locked, right? So you can also have rapprochement because of the high temperatures and pressures that are in place. But even in addition to the rapprochement, if you have very dissimilar metals, this type of interface causes very good joining. So how does it work? You typically have you have a base component that is typically thick, and then you have another component, right? That is what they call the flyer, right? Here is what they marked as the prime component, and it's not touching exactly. It's at a little bit of a distance. Now you have to know what you're doing to do this, right? And it's not trivial. When you hear an explosion, you think it's boom, but it's not really boom. You start the explosion and it starts to propagate. So these people time it very well, such that the two plates are at a distance. When the explosion starts, what you hear as boom starts, and the two parts come together, generating these local shock waves that give you this undulated mechanical interface. And as the propagation front of the explosive charge moves, right? This is the explosives. The explosives were all the way here. This already exploded, causing the bonding in this interface. Here the explosive is in the process of burning, and is bringing these two parts together, right? So now cleanliness is important, but you realize whatever might be going here is expelled too. So it's a fairly robust process. It's used so seldom, right? Well, okay, it's used commonly to make chemical reactors and things like those, but compared with MIG or TIG or the other things we have been discussed, is so much less used that it's not very well understood, right? So the amount of understanding we have for the other welding processes is much larger than this. So not only I don't know it very well, but if you ask questions that are too deep, you're going to see that people start saying, well, if I do it this way, it works. And you cannot ask too many things. But it's quite interesting. there are some theories. Have you guys heard about shaped charges, like the bazooka, right? That actually, although it looks like it's pointy, in reality it's a hollow charge, right? And when the hollow charge hits, right? Do you know how it penetrates the armor? Because at the point of the hollow cone, it generates like a jet of molten metal that drills the armor. That's the way you penetrate armor. So apparently some of that is going on in here, in which this part here is a little bit like the hollow cone of a shaped charge that spits some of the material in and gets caught. And that's how you generate this waviness. But nobody knows for sure. Isn't that interesting? The filler material, you have the flyer that is a clad plate. So typically this is done when you want to have plates, right? So you have one big plate, and you want to, that might be steel, and you want to coat it with titanium. That would be extremely difficult to do by any other means. But with this process, you can do it, because you're not melting the titanium that is highly reactive, and also the titanium and steel don't mix all that easily if they were to melt, right? So in this case, you get it done in 1 second, what would have taken you days to do before. Except that now, to do this process, dealing with explosives, takes 1 millisecond to go boom, and it takes you days to prepare to go boom, right? So you can join, in this case, you can join large areas. This is very different than MIG or TIG, because MIG or TIG, you go with a line, right? This is like a marker, right? When we talked about strip cladding, it's like if you go with a roller, right? But in this case, it's as if you come with a stamp. You just make all this big area. You put this new material all in at the same one. Now, it's good for the similar. We mentioned, depending on the velocity, velocity is a velocity of propagation of the explosive charge. So you typically have explosive experts being involved in this, because although you hear boom, not all booms are the same, right? Some booms went faster than others, and as the velocity of the explosive propagates differently, you would have different types of interfaces. As you can imagine, we're not going to be doing this in our lab, right? Not more than once, at least, right? So you need special places. When I was a professor in Colorado, there was a special mine. The university had an experimental mine, and there is where they would go with the explosions, right? The welding parameters now is not current and voltage anymore, right? It's a choice of explosive. Titanium cladding for steel is a common application in chemical reactors. For us in chemical and materials engineering, that matters. You can make like this huge plate, and then you roll it and make the pressure vessel. I have a video I want to show you about this, but I couldn't embed it.
For real blast.
There you go. All right, that will be another day, huh? You cannot tell me that welding is not awesome. Come on. Roll welding. Funny enough, roll welding is okay, before I wanted to tell you something else. There is something called magnetic pulse welding, in which you get more or less the same effect of like two surfaces like slapping on each other, just because you have like this incredibly strong magnetic coils, which you discharge very, very quickly, and they accelerate one part against the other. So that, if you do that, you can have effects very similar to explosive welding without an explosion. So yes, you can do those in the lab. I think Professor Chen has one of those in the lab, right? So that is used in automotive industry, for example, because you could make two pipes, and if you have the right shape of coils, you can make one like hit the other so quickly that you generate this type of interface, and you do it in an industrial setting, not in an underground mine. All right, so yeah.
So you can do
talking with round configuration?
Yes, but explosive welding, I've never seen it done in round configurations, right? Yeah, yeah. So, but it's a similar principle. They're different, the welds in the end, but they have this wavy interface, right? In roll welding, you try to do something similar to what you do with explosive welding, not because of you would have an explosion, but because sometimes you want to have two big surfaces, right? Two big surfaces together. You would, in that case, you would just roll the two metals, and as you roll them hard or with mechanical deformation, they become bonded. Oh. I think I wanted to say more about this. Roll bonding. Okay, it's funny. Okay, so roll bonding. Okay, anyway. So in this other process, and this is something actually chances are that you have in your house, because those pans that are like they have a copper bottom, but they are those pots that are steel but have a copper bottom, right? The copper is because it's a very good thermal conduction element, right? So the way they do it, like half copper and half steel, is with roll bonding, all right? Okay, so this is what I wanted to share with you about solid state processes. Anything else you'd like to discuss about solid state processes? So next time you're in the lab, take a look at our friction stir welding machine. I'm not certain if we can have a demo for you on that one or not, but you'll see it. It's big and very rigid, yeah.
In the video, we saw what you call stud welding.
Yes.
Is that more or less similar to spot welding?
Okay, so just because you ask, let's see. Topics. Here. This is something I wish I had mentioned before. So your question is about stud welding, right? So that is an arc welding process, which, because we were running out of time, didn't mention, but I'll mention it now. So this is called flash welding, and it's similar to stud welding. What you do is you cause the arc between the two parts, and then you push the parts together. Similar to what we were talking about in friction welding, you have the two parts, and you put them and then you press them. This is that same thing, but instead of being the heat from the friction that generates the localized heat at the interface, in this case, you have an arc between the two, right? That's all it is to it, right? So typically, in this case, you would melt the material, and you typically have no shielding gas. Sometimes you could have gas. Sometimes you would use like a flame, like natural gas in a reducing mixture, right? Is autogenous. The polarity typically is AC. And the applications, right? Here's the stud welding that I was talking about. Applications are things in which you would create the arc between these two, and then you go in, right? And this is a bridge deck. And then you're going to put concrete here, right? And this is what keeps the concrete in place, right? A related process that is not stud welding, but it's based on the same principle, is railroad tracks. You have one railroad track, the other one you want to join them, and what you do is you run a current with an arc, and this arc would generate the heat at the interface, and then you push, right? This is one arc welding process I didn't discuss, which again, it is fairly common, right? It's like what happens is you seldom see it in action, right? Bandsaws, right? When you have a bandsaw like we have in the lab, have you ever thought, how do you make something that runs infinite, right? And okay, fine, you can say I welded. How do you weld it? Not trivial. And you welded using this process, right? Like you put an arc between the two sides and you come together. Have to do it with lots of care. All right, thank you for your question. It was an opportunity to give these slides I didn't use before. Okay, how about if we talk about resistance welding, that is the way you would weld cars. Yeah, and many other things. So we are talking about so many processes, right? Your head is going to explode, but eventually you become familiar with this, and I think this way we're doing about going more or less in a systematic way about how you're joining things and what is the physical process that brings the heat is going to help. We talked about fusion processes that were based on the arc, right? TIG and MIG and submerged arc welding and stick welding, whether we have fluxes or not, whether the electrode was consumable or not. This I just talked about stud welding and flash welding, which is something I had skipped, but that is part of arc welding too. Now, we made a shift, and last class we started to talk about solid state processes, right? And we talked about friction stir welding and friction welding, explosive welding, right? That was very different because in this case we were not melting the material. Typically I talk about solid state welding much later in the class, but this one I wanted to give room in case we did a demo in friction stir welding. Now I want to go back to melting, right, to fusion welding processes. But now instead of talking about let's fuse it with an arc, let's fuse it with some other physical mechanism that will be the electric resistance. So the first one I want to discuss is resistance spot welding. This is the way you weld cars. This is the way you weld pretty much everything that is made out of sheet metal. You will see this in our lab because we have, and Louis, if you help me remember, and Mitch too, we have a little unit that does this. No, it's not as big as the ones that you have in automotive, right? And in this case, you would have electrodes. You have one electrode here, and you have the other electrode here. And this is a sheet. The sheet is coming on this plane out of the board, right? So you put the two sheets. Do you remember what type of joint configuration this is? When you put the materials like this? Lap. It's a lap configuration. And then you circulate a current. And as you circulate a current, the welding happens. And it's super, super interesting, the physical principle, because the current is the same going from here to here, right? And I know you didn't have much of an electrical engineering, but the power, right? Let's see this one. The power is I square R, right? That's the heat generated. So if I have a contact, right, a contact, the resistance is higher. So the heat is generated at this contact point. That is exactly where you wanted it to happen. Now, there's another contact here. But you don't want this resistance to be the one that is generating the heat, right? So these electrodes are copper, which is a very good conductor. They are water cooled, so they are not too hot. And they are shaped in a very special way, such that these electrodes give you good pressure and good electrical contact, and have very little resistance of contact here, right? So this process is almost like a miracle, because you're welding exactly where you wanted to weld, even if you don't see it, because you don't see this. This is inside, right? It's kind of magic.
Circular stuff.
This?
The middle, is it?
This is the melt. This is what they call the nugget, right? So as the current comes here, it generates heat at this interface. This heat creates the melting. Typically, molten metal is also more resistive. So this keeps the heat, and this starts to grow. Now, why doesn't it grow until it touches the electrode? Because the electrode is cooled. So this part of the metal is colder than this. So you have a gradient. So now you have to know what you're doing. This is the way you weld steel cars. In aluminum, this is extremely difficult to do. Aluminum cars are typically not welded with resistance spot welding. Right? Because so they have a completely different construction mechanism. When Tesla made the Model S and the Model X was aluminum. They welded it in other different ways. When Tesla wanted to do the Model 3, they decided to make it out of steel because it's the car for the people, right? It's cheaper. And they started to do this type of welding. But it's very difficult to set up. One of the main reasons why the Tesla was late in delivering Model 3 is that they couldn't weld it. Now they can. But very smart people, but still take time. Some cousin processes to resistance spot welding. One is called projection welding. In projection welding, what you do is you have, like, you make a little dimple in your part. So only that part of that dimple is touching the other surface, and the weld is going to happen right there, right? And then you can press it. Looks like this. There are advantages to do that. In this case, you put some amount of pressure between the two electrodes. The pressure is going to squirt some of the melt out. That's when you do resistance spot welding, you see some sparks flying. No sparks flying probably is a bad weld, because if you have oxides or impurities, they're trapped. Too many sparks flying probably is a bad weld again, right? So those who know, those who live and die by this, they look at a weld and they can tell you everything just from these sparks. But also, as I press here to squeeze out some of this molten metal, I'm going to leave a dimple, right? So resistance spot welding is tricky because it's so convenient, but typically it's not in a place you want to see it, because you're going to see all these little dimples when you weld it, right? Very interesting. So in this case, you can do away with the dimples, right, by putting the pressure and leaving it flat, right? That's one advantage. The other is resistance seam welding. And so imagine the electrodes, instead of pinching it like this, were two wheels, right? And then the two wheels are going to roll, right? The part rolls, and the weld is being generated, like as a continuous seam. Of course, in this case, you do have a melt, but you have no protection, right? This process is typically done without protection. And the reason is, as you generate the melt and you put the pressure, whatever might be oxidized spits out and solidifies very, very, very fast, right? A normal car has of the order of 3,000 welds, right? And each weld costs like cents to do, or less than cents to do, fractions of a cent to do. You go, right? Like you go very quickly. This is not a weld in which you spend a lot of time looking at it and making it perfect. Right? It's exactly the opposite of a pipeline weld. Actually, in a pipeline weld, every weld you take a lot of time, you make sure it's perfect. In car welds, you make sure they are okay. But typically, cars have 3,000 welds, but the car would run in much lower number of welds. It's just like, just in case, they put more welds. Is this autogenous, homogeneous, or heterogeneous type of weld? Autogenous, right? Like because you're putting no filler there. Although again, if you want, you can, right? Everything you want to do in welding, you can, but typically you just run it as is. Very low cost per weld. The current now runs in the thousands of amperes, right? Because we're talking about resistance, but right, like the electrical resistance in a long conductor, you can think, but electrical resistance going across a plate, isn't that crazy? It's very, very low resistance, right? And if power is I squared R, and this R is very small, that means I is very high. Thousands of amps, many thousands of amps, right? So you can make more than one sheet at a time. You can make triple stacks. You can make so many things, right, with this welding process. No problem welding out of position, although you have a melt. The melt is confined to the nugget. So you can weld like this, like this, like this. You don't care. It's not like MIG or TIG, in which if you weld overhead, you're going to see it matters. Right? So this is very easy to do with robots, can be performed manually. Because now this is a spot weld. All you need to do is like make it happen. Right? It's not that you need to be tracking a seam. So this is a pretty interesting type of weld. The welds often have low quality. Remember when we talked about if I cool, if my weld is big, it takes long to cool. If my weld is small, it takes short to cool, right? If it takes short to cool and it's made in steel, I'm likely to have martensite, right? Okay, these welds are tiny. This is all martensite. And you have to live with that, right? These are not like the highly handcrafted welds of pipelines. The exact opposite. This is martensite. Oh, too bad. Let's move on. What else? I can tell you typical applications are automotive, HVAC, white goods. Everything that is made out of sheet metal is likely to involve spot welding. Let me show you a video. Oh.
Resistance welding processes produce coalescence of overlapping workpieces with heat generated by the resistance of the
They're doing it by hand. Doesn't look like it's doing anything, right?
welding current and the application of pressure. Resistance welding is primarily used to join sheet metal stuff.
That's a seam weld, resistance seam
To
welding.
join thin plate. All metals which can be fusion welded are weldable by resistance welding. Resistance welding processes use copper electrodes. These electrodes perform 4 functions. They conduct the welding current to the work, and in some cases, fix the current density in the weld zone. They transmit a force to the workpieces. They dissipate some heat from the weld zone. And they maintain relative alignment and position of the workpieces in some resistance welding operations. Very high electric currents are used to quickly produce the resistance heat necessary for fusion.
See a tail of the weld?
3 principal
I'll teach you how to calculate that.
welding are spot welding, seam welding, and projection welding. Spot welding refers to making welds one at a time between the electrodes. One, several, or many individual spot welds may be required, depending on the application. Spot welding, with the electrodes maneuvered by articulated arm robots, is commonly used to join sheet components of automobiles.
You see
seam
sparks?
welding, coordinated pulses
That is when they squeeze out the metal.
rotating wheel electrodes produce a series of overlapping spot welds, resulting in a lead-type welded joint. In projection welding, the welds are localized at predetermined points by projections, embossments, or intersections. Several points may be welded simultaneously. All resistance welding methods use either semi-automatic or automatic systems. With semi-automatic machines, the operator either positions the workpieces between the electrodes or positions a portable welding gun around them and pushes a switch to initiate the weld. Welding then proceeds according to a pre-programmed sequence. Automatic machines feed workpieces into the machine, where they are welded and then ejected without operator assistance. The typical resistance welding system consists of a control panel, a welding machine with a rigid frame, a low voltage, high current welding transformer, electrodes, leads connecting the electrodes with the welding transformer, controls to regulate electric current, and a pneumatic cylinder or other means of exerting force to the upper electrode arm.
Question to you. I'm gonna tip my hand. I'll tell you it's more, again, like similar to electrical engineering. What do you think you use for resistance spot welding, AC or DC? It's AC, almost always AC. Why? Let's say we want to weld with 10,000 amps, right? A rectifier for 10,000 amps is crazy expensive and probably not all that reliable after all. But if I have a transformer that would transform my line from 60 hertz, right, from the whatever voltage I would get from the line to these 10,000 amps, that's okay, right? Remember when we talked about the difference between Tesla and Edison? Tesla was proposing to transmit the current with AC, so you could use transformers, raise the voltage, lower the current, and have low losses. But DC doesn't work like that. That's why today we use AC in our homes. Edison was proposing we would use DC in our homes. But you cannot transmit the power all too easily. In the case of resistance spot welding, you need so much current that you just might as well run with the same frequency of the line and just have an enormous transformer, right? When we talked about stick welding, if you remember, we talked that some electrodes run in AC too. It's because now, if you don't need 1,000 amps or 10,000 amps, still is the cheapest welding machine, the one that is just a little transformer, right? But now as you go in AC, you would have other problems. All right. Let's see. This is a super cool video you have to see. This is a research video. People were sectioning a weld and seeing how it happens in real life, right, in real time. So you can tell this is quite an old video. One electrode, the other electrode, the two plates, is not so clear. The interface between the plates go here. The current goes here. You see this? This is the zinc. Typically, the steel in cars is zinc-plated steel sheet. The zinc, they say burning off, but it's not burning off. It's just melting. And then you're going to see how it starts melting in there. This is a very high-speed video. This happens in like very short time. This is molten metal. This is molten metal. You see, of course, this is because they sectioned the process so you would see it. Nobody welds like this. But isn't this amazing? And the reason the melt doesn't reach the electrode is because the electrode is water cooled. So as the melting interface moves down, it's encountering faster and faster cooling. Isn't that cool? I'll show it to you again. I just think it's worth it. Zinc has low melting temperature and a high vapor pressure, right? A low boiling temperature too. So it's a problem in the welding of cars because for corrosion protection, you have this zinc coating. But when you want to weld it, the zinc melts and then it boils and causes all kind of problems like porosity. In this case, you do away with porosity because you spit it out, right? You saw in the video how there were big sparks in the automotive line, right? You press, and everything bad goes away. But if you're doing other types of welding, like laser welding or MIG welding, the zinc, you're not spitting it mechanically, and the zinc can cause porosity. I'm sure there are better quality videos somewhere. I'll have to find them. Cool, eh? And all this happens in a small fraction of a second, and a car has about 3,000 of those. Just go, 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 go. Is it a good weld? I don't care. Just go, 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 right? All right. Other type of, this is called electric resistance welding. Some people call it a solid state process. It's not solid state. It's a resistance welding process. And in this, we do this in this province. Some of the pipe in this province is made with this process. So this is an industrial process. It's not something you do manually. It's something for which you need a pipe mill, right? So I'm talking about things of which there are few in the world. It's not that you go to Home Depot and you get your little ERW welder. Electric resistance welding. So this is a pipe mill. You start with your scalp that you start bending, right? And as you push it through the rollers, right? Eventually you have the pipe that is like this little tube. Now you need to seal it, right? And this process is super cheap because you just fly with it. You generate with this magnetic coil. We should have electrical engineering, I think. A little bit prime. This magnetic coil, right, is causing a magnetic current here. Here's the trick. If you believe me that the electrical current here induces a magnetic field that creates a current, the current, if the coil goes like this, the coil in the pipe wants to go like this, the current in the pipe, right? But do you think just like this current goes in circles through a coil, do you think I can make a circle here? Maybe, maybe not, because I cannot jump this gap, right? And there's no arc there. But if you do it right, and this is a trick, if you do it right, you go here, kind of go there, has a point of concentration of the current right there, which gets very hot, just where you have the pressure, comes back here and goes. Interesting, huh? Now, you have to do it right. And to manipulate the magnetic field, this way you have this that is called an impeder. This thing makes the magnetic field force the concentration of current in the pipe here. So sometimes the currents can go other ways and you don't weld, and that doesn't work. But once you have this system tuned up, it works like a charm. And you're just flying this pipe down there, and it's getting welded on the spot. Funny enough, this process is so cheap that people think it's not a high-quality process. For the most part, if you were to weld the pipe with arc welding or other of those processes we have discussed, people would be happier. Now it pains me, because this process is amazing, right? It's almost a solid state process. It's not solid state because you're actually melting here. But as you press it, you're spitting out the liquid. And then you're getting the pipe welded in a way in which you're not going to see a fusion zone, right? This is a very interesting welding process. So you don't protect the melt. You expel the molten metal, somewhat similar to resistance spot welding, right? In resistance spot welding, you expel some, not all of it. In this, you expel almost all of it. It's autogenous. The polarity can be either induction, or you can have DC, in which instead of a magnetic coil, you just put two DC contacts that would run. Very low cost per weld, very high productivity, very expensive equipment. We're talking about a pipe mill here. I'm not talking about a shop. Right? I'm talking about a pipe mill. Evraz can do that. Tenaris can do that. It is not Joe on the corner shop that is going to do this. Typically using carbon steels, people have done it in stainless steels. Typically it's a butt joint, right? Can work with high frequency or DC. So if you're going to use high frequency and using DC, now you'll need some sort of electronic conversion, right? If it was run at 60 hertz, that would be amazing, but it doesn't. So this is typically considered like low cost. Applications, pipes for oil, electrical conduit, pipes for hydroforming in automotive, right? You make little pipes and then as you give them shape by internal pressure. So I'll show you this one last video and we'll go. So this is a pipe mill, right? In the forming line, we get the strip of steel which we're bending until it becomes a tube. Well, there is some fantasy view about the magnetic fields there, but we're expelling the liquid there, right? Don't pay attention to those, huh? And then they bring this tool that takes out the internal burr, right? Well, this is now a pipe mill. It's an integrated operation in which you do the quench, right? And if you control the cooling rate, you get the right type of microstructure. I believe now they do NDT. Okay, there you go. Aerostatic testing, but anyway, so it's interesting. This is yet another type of welding process. So thank you very much. Let's stop here and I'll see you on Thursday.